Hey, what's up, guys? Today we're actually going to be doing another question for the October LeetCode challenge. I think we're on day 6 now. And for this video, I'm actually going to not be playing music. I'm actually going to commentate my solution as I go, my thought process. I thought that'd be a little more helpful and, yeah, a little more, I don't know, exciting than just having music going and coding it myself. I thought this would be a little more helpful to show my thought process and give commentary as I go. Alright, so let's dive into it. Yeah, first time doing this question. I've done similar questions before, but not this one. Okay, insert into a binary search tree. You are given the root node of a BST and a value to insert into the tree. Return the root node of the BST after the insertion. It is guaranteed that the new value does not exist in the original BST. Notice that there may exist multiple valid ways for the insertion as long as the tree remains a BST after insertion. Okay, and you can return any of them. So yeah, the one interesting thing here is that, yeah, we're guaranteed that the new value does not exist in the original BST. So you don't have to handle that edge case or scenario. So they give us some examples here. I think it's a pretty straightforward question to understand that you're just inserting a value into a BST and returning a resulting BST that still satisfies all the conditions of a BST. Okay, so for me, just right after reading this, right off the bat, this just screams recursion to me. A lot of tree questions, lend themselves very naturally to being solved in a recursive manner, just because you can repeatedly use the same process on left and right subtrees as you go down the tree, as you navigate the tree, and yeah, recursive solutions tend to be usually the way to go for most BST questions. So yeah, that's what I'll be using here, most likely. Some constraints here, yeah, nothing too conspicuous here other than this, yeah, so we don't have to continue the case where value is equal to the value of the node that we're currently evaluating. That won't happen. Okay, so we don't have to worry about that. So here we go, we're given the class structure for tree node. It just has a value attribute and a left and a right attribute, and the only thing we need to pass in the constructor is the value. Well, it defaults to 0, but we're gonna have to use tree node to actually make a tree node, and we're gonna have to pass in the correct value parameter to initialize it correctly. Okay, so let's dive into it. Yeah, so here's the function that's going to be called, and like I said, we're going to be using recursion, so we're going to be calling this function within itself, just with different parameters. So that's where the recursion comes in. Okay, so if root is null, let's do that first. If not root, then we just return a tree node object with the value parameter as our value, this value argument. I think that's it. And then we have to consider the cases where we need to either insert it into the left subtree or the right subtree. So if root.val, and we're safe to do this now because root is guaranteed to not be null, so it's going to have a value attribute. So if it is less than the value that we're trying to insert, trying to see an example here. Trying to insert 5. Yeah, so if we were trying to insert like 8, for example, then yeah, we have to process the right subtree. The left one stays the exact same. Then root.right is going to be this function called on the right subtree. I think this should work. And then otherwise, because right, this otherwise would also capture the condition of root.val being equal to val, but we're told that'll never happen. So this we can say that this condition will be met in the universe of this question when root.val is greater than the value that we're trying to insert. So then we just do the left subtree. And then once we're done that, we just return roots. I think that should work. Let's give it a shot. We're good there. Can we even do this? I think we can. That's kind of cool. Yeah, I think we're on the right track. Let's submit this and see if we got it right. And there we go. So that's how you would do a question like this. Yeah, recursion. And honestly, with BSTs, or sorry, just trees in general, or any sort of like graph structure, it makes a lot of sense to use recursion. It's a good weapon to have in your arsenal. Runtime complexity. Well, we're only going down. The maximum number of recursive calls we can make is the depth of the tree. So it'd be O(n), where n is the depth of the tree, I would say. Space complexity. Let me think for a second. It's definitely going to be O(n) as well because of the stack frames that have to be saved in memory. I'm trying to think if I'm missing anything else. No, I think that's it. So anyway, yeah, hope this was a little more helpful than just having, music going as I solve this in silence. Anyway, yeah, that's it. Thanks for watching.